Okay, so let's begin this lecture on quantum statistics by just reminding you a little bit about what happened in the previous lecture, on the one on Boltzmann's entropy, just in case you didn't watch the introduction to this one, so to make sure we are all on the same page. Okay, so remember what happens is you have a gas of non-interacting identical particles, okay? And what we did to describe the state of the gas, the microstate, the specific dynamical state that the whole gas is in, because the particles are non-interacting, you can just look at what each particle is doing independently from all the others. Okay, so what each particle is doing independently, to look at it, well, you have to go to the single particle phase space, okay, or mu space. So what is this? Well, it is a space where you have a set of orthogonal axes, if you like to think about it geometrically. If your particle, for instance, has f degrees of freedom, you have two f orthogonal axes. For instance, for the case of a monatomic gas, you have three generalized coordinates, x, y, z, if you like, and then you would have the associated momenta, px, py, pz. So you have a six-dimensional space. If you give a point in the six-dimensional space, you are supplying all the information you need to know. You are supplying what's the generalized coordinates, what's the position the particle is in, and what momentum it has, where it's going to exactly. Okay, so that fully specifies, say, the state of particle 1. You have to do the same with particle 2, 3, 4, 5, until you get to the large number of particles that your gas has. Okay, capital N. So these coordinates are continuous, okay, and then you would like to count how many microstates, or you want to label microstates and distinguish them from one another. In order to do that, if your coordinates are continuous, you have no other choice other than discretizing your phase space. Okay, so you take the phase space and you break it down into little phase space cells, okay, like you see there. And they have a small hypervolume, but it's a finite one. It's not infinitesimal, it's finite, but small. Okay, and all the dynamical states that just happen to fall into any single one of these little hypercubes, you are going to count it as the same thing. So it's only one state, okay, or one microstate, if you like. So even if the total number of microstates that your system may be in, I mean, a single particle of your system may be in, it will be some number that you can count. Okay, we call that capital M. So there are capital M of these phase space cubes, and any given particle in your gas can be in any one of these cubes. Okay, in particular, you can go cube by cube and ask yourself how many of the particles in the gas are right now in, say, this cube, and then in this other cube, and then in the other cube, and so on and so forth. So you end up having an array of numbers. Like there are n1 particles in the first phase space cell, n2 in the second, and there you go until you run out of cells, nm. Okay, so this specification is what we called in the previous lecture a macrostate of the system. Okay, it's one possible macrostate of the system. Remember, macrostates depend on really what you can measure, what you can distinguish. So this would be one macrostate, because you are losing already some information. If you want the full specification of the state of the system, you would need to say something like, say, particle label. Okay, label. And you have to supply the phase space cell that each particle is in. Okay, so phase space cell. So if you specify like this, so particle 1 is in cell 32, and particle 2 is in cell like 1005, and cell K is in whichever, like 2, and so on and so forth. That will give you the full specification. So you know where each one of the particles, of the n particles that make up your gas, is sitting at the moment. But now we are not saying this, we are saying we are forgetting about the particle labels. Okay, so we just count how many times each cell appears in this column here. and this is what we are supplying. So we are forgetting some information already. When you don't have the full information about the state of the system, you have a macro state. Okay, so that's one possible way of making a macro state, and we use that, and in particular we calculated how many different configurations, how many different microstates are compatible with a given specification like this of macro state. And we counted them, and we established that this specific macro state has statistical weight equal to the product from 1 to capital M of n factorial divided by ni factorial, okay? Which we wrote explicitly like this, n1 factorial up to nm factorial, okay? So that's the different number of arrangements of different microstates of the system that are compatible with this specification here. Now, this kind of specification of a macrostate is not the only one that you may have, and it's actually not the most common one. Most often, what you know about the microstates of your system is not exactly how many different microstates there are. You just know the energies, the different energy levels that, or energy values that your particles may take on. Okay, so that's the usual thing that you know. So there are, or there could be, it doesn't need to be the case, but there could be several phase space cells in your single particle phase space that have the same energy. Okay, so if you just say energy something, you may not be singling out one phase space cell. Okay, so it's a bunch of them. So it could be a region in phase space with all of the cells having the same energy. So if instead of giving this specification for a macrostate, you give this other specification, n energy 1 up to n energy little m, where the different values of energy that your system may possibly have are E1 up to E little m, okay? And, sorry, that's not what I wanted to do. So this specification is also a macrostate, but it's a macrostate with less information than we had before, okay? Because now we are losing track even of the specific cells in phase space. Not just the labels of the particles, but also the specific cells. We only know in which subgroup of cells each particle is falling into. Okay, and there may be several cells, like I said, with the same energy. Let's give a name to that, or let's give a notation for this. So the number of cells with energy E1, we are going to call it G of E1. And the number of cells with energy E2 would be G of E2, and the number of cells with the highest energy is GEM. Okay, so if all of these numbers are equal to 1, then this EM is actually equal to capital M, and this specification is identical to the previous specification, because we are saying that given the energy singles out one specific cell in the phase space. But in general, these G's are going to be larger than 1. Okay, maybe not all of them, but you know, some of them could be larger than 1, and actually some of them could be a lot larger than 1. Okay, so certainly this macrostate is different from the other one, and what we would like to do now is to calculate, just like we did before, what's the statistical weight of this type of macrostate. Okay, so let's do it. And to do that, well, I'm just going to try to follow closely what we do in the lecture notes. So I will kind of repeat somehow the calculation we did, or the argument that we used in the previous lecture when we were trying to calculate the statistical weight of this other type of macrostate. Okay, so what we said then is, okay, I have a bunch of particles in a box like this, okay, and how many particles I have? Capital N, so a large number of them. Let me just make the drawing. Okay, so these are all my N particles, and I want to pick these particles and bunch them, or what I wanted to do before is bunch them into the first phase space cell, the second phase space cell, and so on. So what I want to do is to see how many different ways I can pick N1 particles out of this box. How many ways there are? Well, for the first particle you have, remember, N choices. And for the second particle you have N minus 1 choices, and so on and so forth, the last choice you make for the first cell, okay, was n minus n1 minus 1, okay, and you don't really care what's the order that you are picking your particles in. Okay, this is something you don't care. You just care about the choice. So, for instance, imagine the choice I have in mind at the moment is this one, and then I pick that one, and that one, and that one, and that one. So this choice would be the same if first I pick this one, and then I pick that one, and then I pick this one, and then I pick the other one, or if I pick them in any other different order. What I'm talking about is I am picking those particles that are highlighted there, okay? And I don't care in which order I pick them, because then I'm going to bunch them into a single phase space cell. This is what we did before, okay? Now, instead of bunching them into the same single phase space cell, now we have a choice. We have to put, because, just rewinding a little bit, because we don't care about the order, we have to divide by n1 factorial. This is what we had seen in the previous lecture, okay? But now, all of these particles don't go into a single cell. They can go into any cell that has energy E1. And how many cells like that are there? There are G E1, the degeneracy of the energy level 1. This is called degeneracy. Okay? So for the first particle out of these N1 particles that we are picking, we have to multiply this by how many choices we have for the first particle. We have GE1 choices. So there are GE1 cells in the single particle phase space with the energy that we want. And in principle, we could just throw away our particle into any of such boxes, okay? Now for the second particle, we pick how many choices we have, the same, okay? And for the last one, well, the same, okay? So when it comes to the choice of our first group of N1 or NE1 particles out of our box, we have a total of n factorial, if you want, divided by n minus n1 factorial. Okay, this ratio makes this numerator here, and this divided as well by n1 factorial. Okay, and then here I have a product of g e1 n1 times, which is gn1 to the power n1. That's for particle 1. Okay, now for particle 2 it would be very similar, but instead of starting with n, we would start with n minus n1, and we would end up in n minus n1 plus n2 minus 1, and so on and so forth. But here, you know, the number of different states that then we can throw away our particles into is GE2 to the power of n2. Okay, and we carry on doing that until we run out of different possible energies, just like we did in the previous lecture. Exactly the same thing. Okay, and what we get when we multiply everything together is a different statistical weight, was just slightly different, where we have n factorial, and then the product from I1 to the number of different energy states that we have. And here you have the G EI to the power of Ni, this kind of factor. And in the denominator, we just have the same thing we had before, Ni factorial. Okay? That's what we have. So the only difference with what we had seen in the previous lecture is this G that appears in the numerator. Because remember, if this G is equal to 1, then we are in exactly the same situation. There's no difference. But if G is larger than 1, then there is a difference. Okay? That's why we are adding this. In the way of counting the microstates, there would be a difference if there's degeneracy. Okay? So this is the new statistical weight. And the name here stands for Maxwell-Boltzmann. Okay? It's like the classical one. Okay, so this is now the new statistical weight that we have. Just a slight modification of what we had before, because now we are choosing to define macrostates slightly differently. Now, well, let's see now what would be the equilibrium entropy, or the equilibrium statistical entropy, using this statistical weight. Okay, if there's some change on it, there will be, of course, a small change reflecting that there is degeneracy, and we want to see what that change is. So remember, the Boltzmann entropy, let's write it like this, is proportional to the logarithm of the thing that we have at hand. Okay, and the logarithm of this thing, let's just write the logarithm. So I'm going to divide this by k to get rid of the k, which is multiplying everything. What we will have here is just logarithm of n factorial plus, then we have the sum, so this product becomes into a sum. I'm going to write it like this for shorthand notation. I'm going to write it like this. And here I have the logarithm, I have ni logarithm of g ei, the degeneracy of each of the states, and here I have minus, well, let's just write it, let's just write it in the next line, maybe, and then minus the logarithm of ni factorial. Okay, now remember Stirling's approximation, so we are going to assume that the number of particles in each of these different possible energies is going to be large. Now I'm making here a simplification of the notation. Here, I'm referring to these n's as n sub ei. Okay, this is like 3 levels of indices, and I don't want to carry on doing that. I just wrote the old macrostates here for reference, but in this chapter, every single time we specify a macrostate, we understand that the meaning of the first integer that comes into this array is the number of different particles that are sitting in one of the possible energy states, and not phase-space cells. Okay, so we are going to just simplify this notation into that one. Okay, so don't get confused. In this chapter, in this lecture, all the time we are talking about the number of particles that have certain energy. Okay, so that's why I'm using ni here. Okay, so anyway, just like we did in the previous lecture, I'm going to assume that the number of particles having any specific energy is going to be very large. Okay, so I can apply Stirling's approximation, and this is approximately, or quite well approximated, by n log n minus 1 plus, and here we have the sum over all energies, and well, the first term really doesn't change, right? So because there's no factorial here to be approximated, logarithm of that, but here we have ni log ni minus 1. So you cannot really see that. Let me just move it a little bit like that. Logarithm of ni minus 1. Okay, so this is, the whole thing is inside of the sum. Okay, so this is the statistical entropy, just divided by k, because I don't want to write k all the time, and I want to maximize this thing, under 2 constraints. So remember, I'm always thinking about this situation of Clausius theorem. So I'm thinking of a closed system which is isolated, so energy doesn't change, and I want to find what's the maximum entropy, because I know that the maximum entropy in such system is the equilibrium entropy. It's the entropy at equilibrium. Okay, so what we want is the equilibrium entropy. And how do we do that? Remember, we use the method of Lagrange undetermined multipliers. So this is the thing we want to maximize. Okay, and what are the constraints? Well, there's one constraint that I write it like this, that the total of particles in any energy, they have to sum up to the total number of particles, which is conserved. And then I also have a second multiplier quantity, which is that the energy of the system, so the number of particles in each energy level times the energy of that level, this sums up to a constant internal energy U. Okay, so that thing, if I take this this variation, it has to be equal to 0. Okay, that defines where the optimal that we want to find subject to these constraints is sitting. Okay, so let's do it. The first term we have already evaluated up here. Okay, and we just have to take the differential with respect to n. What we get is the sum over all ei's. This variation of ni, what we have from the first term is the logarithm of the degeneracy of the corresponding level. Then from this term here we get minus logarithm ni term. Then from taking the differential into the logarithm, what we get is just 1. Then from this term here we get a minus gamma times dn, which is outside, and here we have a minus beta ei dn, which is outside. This whole thing has to be equal to 0. If we want the whole thing to be equal to 0, then this bracket has to be equal to 0, because this dn is arbitrary. Okay, so now let's see what happens. Just like we did in the previous case, this 1 plus gamma, I'm going to call it alpha, just for simplicity. So what you have is that the logarithm of the gi divided, well, let's just change the sign of the whole thing and say the logarithm of ni divided by gei. This thing has to be equal to the rest that I'm putting on the other side, which is the alpha plus beta ei. Okay, so with a minus sign. Okay, so there is the minus sign there. I exponentiate the whole thing. What I get is that ni equals g of each level divided by e to the alpha times e to the beta ei. Okay, so you see that the only difference with what we had found before is that this was equal to 1 before. Now it's just sitting there explicitly. Okay, so this is the new, if you like, occupation number of each energy level that is guaranteed to maximize the statistical entropy when a system is isolated with a certain internal energy. The whole analysis that we did in the previous chapter still applies to this. This doesn't change any of the thermodynamic analysis that we did. So this beta, we know it's the inverse temperature. Okay, that's the same thing as we discussed before. The only thing is that because we are specifying states differently, we get this degeneracy there. Okay, so that's the only difference, and this occupations is what we call the Maxwell-Boltzmann occupation. Okay, so when we have a system of non-interacting identical particles which are distinguishable in the classical case, they distribute in the different energy levels when they are in equilibrium according to the Maxwell-Boltzmann occupations. So each energy level is occupied by Ni particles when it's in thermal equilibrium, where the temperature appears in this beta here. Okay, occupations. Okay, so that's how identical distinguishable particles would distribute like in equilibrium. But if you are in quantum in a quantum mechanical situation, it could be that you are dealing with identical particles which cannot be distinguished. This is not that it's hard to distinguish them, it's that fundamentally they cannot be distinguished at all from one another. Okay, so now we're going to see what happens if you can't distinguish the particles. Of course, you can expect that this thing will change, and therefore the occupation we get in the end will change. But let's see how it changes.